Okay, so let's resume. So I promised that I'm going to show how to analyze this algorithm, discrete version algorithm, but using primary dual. Okay. So we need to write down integer programming and the linear programming and its dual for the analysis. So, okay. Minimum cost. So let's do this. Okay, this is the integer programming to capture this skew rental problem. So Q means Q equals 1 if and only if we buy. Okay, and then ZT equals 1 rent at time or day t, on day t. Okay, makes sense, right? Then, if we buy, then we have to pay cost to k. Okay, and for every day we rent it on day t or that time t, we pay unit cost by. So 1 times ct. Okay, but what is it? Why did I put this big X here? It's the same as small x, but I put this big X, uppercase X, because small x maybe I don't want in the small x get confused with the variable in the integer programming. Okay, this big X is the same as small x. Okay, just keep in mind that. And then also this also makes sense by at any time t, either I should buy it or rent it. Okay, so then I should do it for every time until day x. Okay, this means as I said before, this is a set of 1 to x, and of course in the QZT these are indicator variables, meaning that it will be either 0 or 1. Is that clear? Okay. And then but now we are going to relax this, to use primary dual, we are going to relax this into linear programming. Okay, so actually let before doing so we are going to make this linear programming, and then this will become between 0 and 1, right? But however, to minimize this objective, there's no reason to set Q or Z more than 1, right? Okay, so therefore, this 1 will be redundant. So I can simply say that that's fine, because the optimum solution to this linear programming will never set Q or ZT value Z2 more than 1. Okay? So, yeah, this is integer linear programming. Okay, now let's think about its dual. Oh, by the way, before I talk about dual, let's don't forget that this is an online setting. Okay, I don't know this value x, so you can only see the part of the linear programming. Okay, this is the picture you will see at the end of the day. at the end of the game, right? But what you see is that in the beginning, every time t, you see a new variable, right? So so far now I've seen a z1 through zt if I'm on day t, but tomorrow I'm going to see, if I'm still skiing, I'm going to see a new variable, okay, along with the new constraint. Okay, and this new variable will be added to the objective. Okay, so it's kind of the linear programming will kind of expand over time. Make sense? That's the difference. But anyway, so then now it's time to think about it's a dual. So this is primal, and we can think about its dual. Okay. So I want to use the same notation. So let's okay. So let's say that we use say yt for its dual variable. Remember that we define dual variable for each constraint. So I define yt. Okay. Then it's a minimization. So dual will be maximization, right? So it will be max. Yt and t will from 1 to x, right? And then okay, so okay, let's do this again using principle, right? So what did you do, right? We have you combine the left hand side of the constraint using this multiplier, right? Okay, and then if I regroup this, right? Now I want to rewrite this as the what is the coefficient of q, what is the coefficient of z, right? Okay, then the coefficient of q is this, right? So I'm going to have right derivative from 1 to x is this coefficient should be n most this coefficient, right? This n most k. Okay, this comes from this variable q. And the second constraint y zt. If you look at the coefficient of zt, we have a coefficient y. The coefficient is yt, but it's 1, right? So yt must be n most 1, right? So again, this corresponds to the primary variable q, and this corresponds primary variable zt. Okay. And this we have this for all t n most x. Good. And then okay, of course we want to it's non-negative. Make sense? Any questions so far? Good. So okay, this is what I have. This is a dual. Please simplify. So then again, it's also online version. Therefore, you don't see this whole linear programming a priori. You are going to see it over time. So what happens here? So at time t, you have only seen variables x, y1 through yt. If you skip again tomorrow at time t plus 1, you are going to see a new dual variable yt plus 1. Okay, you will see more dual variables introduced over time. Okay, and they'll be added to this constraint, right? Until time t, you have seen okay, the summation is from y1 through yt, but tomorrow I also need to add yt plus 1, right? So it changes over time. Okay, also x, this x changes, right? Okay, so any questions so far? It's good? Okay, so I'm glad that you're following this linear primal integral. Okay, the algorithm is kind of simple here. I'm going to kind of sketch it. I'm going to ignore some calculation, but I decided twice, give you the whole details. Okay, this is the algorithm we're going to use. Initially, Q will be set to 0. Okay, I don't buy. Okay, at the beginning, but while x increases by 1, do this is what I'm doing. Okay, so Q is my Q is the purchase so eventually Q, okay, if x becomes a large number, right, eventually Q will become 1. Okay? So now it shows that, okay, so as x increases, I'm going to increase Q by this much. How much? 1 over k times the current value of Q plus 1 over e minus 1. So you can see this exponential like increase here. And then, okay, z over x is of course, now what I'm doing is that I'm just setting this, z and y variables, right? Because, to make the others go through, I need to set up the primal and dual variables. Yes?
Is that e to the minus 1 or e minus 1?
E minus 1.
Okay.
Just, yeah, thanks for asking. So if you have any questions about my handwriting, so, please. I know that my handwriting is terrible, so I would not be offended. So I've seen very few people who have a worse handwriting than I do. So, okay, good. The algorithm is really defined, right? So basically, this QT, right? Delta QT will become, PT, right? This is like a, so far I've purchased, this. So far I purchased this with some probability, and now this is the, today I buy with this probability delta Q. Okay, that's the interpretation. Does that make sense here? Okay, good. Then, so let's see why this primal dual gives the desired analysis result, namely E over E minus 1 competitiveness. So for the analysis, we are going to keep track of the change of the primal and duals here. This is online setting, still for the objective will change over time. And the new constraints, the new constraints added over time should be must be satisfied. Okay. So, okay, the first thing we want to check is the feasibility. Okay. So does Q, right? Does Q itself will define will give us the algorithm, but we also define set up this z and y by z and y for analysis, right? So we are going to show that z, q, y, all these will satisfy all the constraints. Okay. Okay. So there are only three constraints here. This one, right? So let's first think about this, right? Q plus zt is at least 1, right? This is obvious, right? Because of this, right? At time t, when x equals t, right? So I set x zt equals 1 minus q, right? Okay, so let's make some observation here. Q only increases over time. Agree? I never decrease Q. I only increase, and then once Q becomes 1, then it's the end of the game, right? Okay, good. And second here, Z I'm interchangeably using time and day, so don't get confused, okay? So I'm setting ZT at time t, and never and once I set zt variable, then I don't change at all, right? Because as I said, at time x when x was t is that, and then at x becomes t plus 1, I set z value accordingly, right? So that's it, right? And same yt, right? yt zt, they are set at time t, but I don't change them at all afterwards. Okay, so then now why is this true? At time t, q plus zt equals 1, right? That's how I set this, right? Q plus zt equals 1, right? Afterwards, q only increases, right? Therefore, it remains satisfied. That's the constraint I want to satisfy, right? Done, right? Good. This holds for all ty I've seen. Okay, now this was one, and let's think about the second one here. Like this, right? Actually, let's first think about this simpler one, yt. This is obvious, right? Because that's how I said it. Why this is 1, right? So this is obvious. Okay, the third one. The third one is a bit tricky because I need to make sure that this, sum of all yt variable, right? This should be at most k. Okay. So that's how I need to, set, this. And so I need to make sure that the summation never exceed k. Okay. So I actually need to do some calculation. So from this. I'm going to put like qt here because the q changes over time, right? Okay, so qt, if you solve this, if you solve this recursion, okay, then you can get it's easy exercise. From here, you can obtain that it's a 1 over c times it. Okay, you can show this. It's a really simple calculation. Okay, then we can just plug this in here. T plus 1 x yt, right? And it is, what is this, right? It is, the ratio is 1 plus 1 over k. So you know this, right? If you have a 1, say like, I don't know, say, let's just say u, let's use u. And this is, yeah, okay, good. So a times I minus 1, I to the last term. Okay. So I mean, you can do the same here. The ratio is the 1 plus 1 over k, and then the last term will be x, right? And 1 over c minus 1 over c. Okay. Then doing some easy calculation here. C, I'm just plug in here. This in y. K over c. So what is this? Okay, so see here something. So okay, so and then okay, so sorry, so I have to set the. Oh, okay, okay. So okay, so let's set this k here because after time k, I'm not going to buy it, right? It's just, that's the end, right? So I only need to add up to k, okay? So therefore, this will become k, and you see this is like a log e, right? Okay, so e minus 1 over c. This will be 1 over k minus 1 over c, right? So I think what did I do here is c. What is c here? Sorry, excuse me. Oh, I see. Okay, sorry, okay, sorry, here. Okay, by solving this, I get this with c equals e minus 1. I'm sorry, okay? Okay? And then, this becomes what? This cancels out, right? K. Did I make something weird here? What did I mess up here? Okay, minus doesn't. Oh yeah. So it's good. Okay, it's a. You can see that it's almost k, right? I mean, if you just do more simple, more I say assume that this is e, but you can just do more like detailed calculation. So as desired, we show that is almost k. Okay. Good. So we show that all constraints are satisfied. Okay, now it remains that actually the cost we buy. I mean, this is the cost we buy, right? Eventually we buy. We eventually when we buy it, we pay k times q, right? So, and then this will be the renting cost. So, can I do this? Okay. The primary cost is algorithms expected cost. Right? That is a linear point, right? So for sure, right? So what I want to show is that this is at most e over e minus 1 times the dual cost. Okay? With respect to xy, x dv of xy z q. Okay, we define the x y z q, and we want to show that actually, we have this. The primal cost is at most e over e minus 1 times the dual cost, right? Okay, then, remember that this LP cost phi, LP primal cost, low bound is the optimum, right? And LP primal is low bounded by LP dual's cost phi. Therefore, if we show this, right, this would imply that it's at most e over e minus 1 times the optimum. Therefore, it will imply desired computed ratio result. Okay. Okay. So let's see why this is the case. So it's actually very nice here. So we are going to see the change of the dual and primal. So what I'm saying is this. How much primers cost changing daily at time t? At time t. Okay. So what happens here? So you see, we increase it at time t. We increase this by delta q, right? So it'll be 1 over k times. If the q was the current value, I'm increasing my purchasing probability by this much, right? So therefore, I have to pay this will be the increase of the q, right, in the objective, right? Delta, right? But you have k coefficient here, so here, and then and also zt, right? I said that I get new zt here, right? And I said zt as 1 minus q, so it'll be 1 minus q. So again, this comes from zt, right? And this is a change of q. So this will be the change. This is how much the primal cost increases at the moment. Does it make sense? Any questions? Any questions about this? Okay. So I don't like the way you're looking at me. So let me explain this again. Q increases over time, right? So at time, okay. So what am I doing here? Q is to simplify the notation. I'm just looking. I actually I'm using Q denote to QT minus 1, right? So what's the value of Q at time in the previous time step? Okay. Now from QT minus 1, I'm updating. I'm increasing Q, right? This QT minus 1 becomes QT, right? This delta Q is this value. How much I increase it? Q value, right? That's how I define delta Q. Right? So therefore, this is the objective, right? Before it was k times qt minus 1, but now I have to pay k times qt, right? Therefore, I have to pay k times, k times the increase of q, right? Delta q. That's why I have to pay this more because of this term, the first term. For the second term, I don't change z1, z2, all the terms, right?
Yeah.
But I'm adding new term, zt, right? Zt is set to what? Zt is set to 1 minus q, t minus 1, right? 1 minus q. So I'm getting this new term, zt, right? That is added to this sum. Yes? So this will be the increase of the primal constant at this new time. Agree? Good. So this now it cancels out, right? And then it's then Q will cancel out. Good. So this will be just E minus 1, right? E over E minus 1. Beautiful, right? And then the change of dual cost at time t. This is really simple because we are adding. We don't touch the old y variables. We are only adding new variable yt. Okay, and it's set to 1, right? It's just 1. This will be yt. Right? It's 1. Okay. So at every time, the dual increases by 1. The primary increases by e over e minus 1. Both starts from 0, okay? So at the end of the day, the primary cost will be e over e minus 1 times the dual cost, as we desired. Okay, so we have shown this. Okay. Any question here? Good. So for the remaining time, I'm going to cover the second example of online algorithms. This is this example is caching and paging. Caching or paging. So let me quickly remind you. The problem is that we have a cache of size. Okay. We have a limited size of cache. Okay, that's if size is infinity, no problem. You don't have to anything here. Okay, but we have limited size. Okay, and then there are n pages, a sequence of pages. I'm sorry, not pages, a sequence of requests for, to be more precise, it should be requests pages. Lines. Okay? And if the page you requested is in the cache, happy. No problem, right? Otherwise, evict one page in the cache. To fetch the requested page into cache. Incurring a page fault. Okay, so it's important here. Page fault. If something in this request is not in the cache, page fault occurs, and you have to pay unit cost. Okay, here, so the goal is to minimize number of page faults. Okay. So let me give an example. So because this example, I'm going to use this example later, so I'm going to put this clearly. 5, 3, 5, say 4, 5, 3, 2, 9, 9, 3, 5, 9, 2, 3. Okay. It's a sequence. Okay. Let's say the k equals 3. All right. So I can store at most 3 pages in my cache. That's my bag. Right? That's my limit. Okay. It's a sequence. So at the first time, these are the index, page index. Okay. Page 5, page 3, page 5, 4, 5, and so forth. Right. Okay. So let's see what I can do here. So I have limited cache here. So I can store 3, okay, the size 3 of 3 pages in my cache. 5 comes here. It's not my cache. I mean, there's nothing I can do here. I have to fetch it, right? No matter what, I have to pay unit cost. Page fault occurs, and 3, okay, split it. What can I do, right? 5 is there, okay? So I don't pay anything. It's okay. When there's a page fault, let's put this, slash here, right? So one page fault, right? But it's okay, nothing. And 4, I patch here, right? 5, still there, right? So nothing. 3, no problem. 2, now page fault occurs, right? And you can see that at this point I must evict some page here, right? Okay, so what do you want to evict here? 4. Why?
Because 4 is only one time.
Oh, it's a good question. It's a good observation, right? So, okay, let's actually just try to be make her observation more like stronger. Okay, so okay, suppose you know the whole sequence of this page requests a priori. It's not possible, but let's assume that we know that. Okay. Then, what's the optimal choice in general? When you are forced to evict a page, which page would you evict? No. That you'd use that. You'd use that if you don't know the future. But you know the future. I'm assuming that I know the future. But what you said is, the LRU, least recently used policy is it's a commonly used policy when you don't know the future.
If the occurrence is the lowest and the least.
Okay, so let's I think you're almost correct. So I'll be slightly formalize what you're saying. So I'm going to use evict. So offline, by offline I mean that we know the whole input sequence a priori. In this case, evict the page request the farthest in the future, right? So okay. I mean, so in this case, 4 is great. Yeah, 4 is not even used by, but if 4 is still requested in the future, then I still evict for page 4 because that's the page that will request the farthest in the future. Okay. I mean, the whole point of caching is that I want to keep pages in my cache that I believe will be used soon, right? So this makes sense, right? And actually, this is optimum. This algorithm is optimum, and this algorithm is called Belladin. This algorithm. Okay. I mean, it's kind of. I'm not going to prove it, but it's an easy exercise to prove this, and this is actually taught in the operating system course, undergraduate operating system course. So I'm not going to cover it. But anyway, of course, now the problem is that we don't know the whole input sequence, right? Okay. So then we have to estimate, right? What's the page that's that's the page kind of that will likely request the farthest in the future. I have to somewhere I don't know the answer, so I have to estimate, right? Guess. So people actually use one of the algorithms. One of the most commonly used algorithm is LRU, which stands for least recently used. Okay. So the idea is that if the page was used long time ago, maybe it's not going to be used for a long time. I think makes sense, right? You use the past to predict the future. So in this case, what do you do? So, okay, if you receive 3 here, right? Then, okay, in this case, you would evict 3, right? But that's not good, right? Because clearly evicting 4 is better choice. Because you see a suboptimal choice here. Make sense? Good. Anyway, LR is pretty like much well, it's very common algorithm, but anyway, it's a suboptimal. Okay. So throughout this lecture, we are going to kind of define rounds for an analysis. What is rounds? Okay, round is we will recursively define rounds, and round is a round is a maximal subsequence of a request. Request and most k pages. Okay, so let's do exercise here. So I start from here. So count 1, 2 different pages, right? 3 different pages. Still 3 different pages, right? Until 3, and then now you see, okay, if you include this, right, then it'll be 4 different pages, right? So let's cut here. This is one round. This is round 1. Right, so I'm going to recursively define. So this is a new the new round starts here. So okay, 1, 2, 3. Now okay, if I include this, I get 4, right? So I'm gonna cut here. And then okay, then where should I cut here? Here, here, here. Between 2 and 3, right?
2 and 3.
Good. Yes, then. Yeah. This way. So except the last round, every round will include exactly k different pages. Okay, and this has nothing to do with the algorithm. This is this is just defined by the instance. Okay, any questions over here? So then you may wonder, why do we define these rounds? Because it kind of gives us a very nice view that where you are forced to make a page force. As an exercise, let's see. Let's look at the LRU's performance. So, the really easy lemma is this, right? Lemma, what's I want to say this. It's okay, lemma. I claim the following. So LRU makes at most 1 page fault in a round. Fix a round, then LRU makes at most 1 page fault per each page. Not per request, but page, right? So this will imply that it makes at most k force in a round. Okay, by definition, right? Because each round includes at most k different pages. Therefore, at most it'll make a k page force in a round. Make sense? So let's see why it is true. Do you see why? LRU makes one and most one page for each. What happens if it makes two page faults for the same page? So, like I say like a page I was requested here, and then later it is requested again, right? So what happened here? So, okay, it was requested, right? Therefore, because of page I, there was page fault. Okay, so I had to evict something, right? This is what I mean. It is. So I had to evict some pages. That's what I put this, up arrow, and then later, because this page, right? I evict another page. Okay. Can this happen, right? So okay, I mean, sure, it's possible that I can be requested later again, right? But then if page fault occurs because of this page I, then it must have been evicted between these two times, right? So at some point, like say for example, like a J was requested, right? Another page J was requested, and this guy evicts page I, right? And then later I is requested again, or therefore page fault. This situation, right? Now let's see why. How can this happen, right? So it evicts page I in LRU. This algorithm. Well, recall that LRU evicts page. That was the least recently used, right? So what does that mean? So like if you look at the cache, right? Like there are like other pages, right? Say like let's just say like U1, U2, like there are other K-1 pages, right? That are more recently used than I. That's why J chose I as a victim, right? I mean, if there was if there was if there was any page other than I that was used longer, old, that was used before I, then either LRU would have evicted that page, right? Therefore, you should be there must be other like K-1 like other pages, right, sitting in the cache, right? So then, what does that mean, right? Think about this I, page I, and these U1, U2, UK-1, right? These are K-1 pages, right? One page, right? And J page right here, right? Then it contradicts the definition of round, right? Because you have seen here K plus 1 different pages. So in one round, this cannot happen. Agree? Good. Okay, so LRU makes most K page faults in a round. Now let's think about okay, so because we want to see the, okay. So now I claim that opt also makes at least one page fault per, in a round. You agree? This should be easy to see, right? You see, right? Okay, if you look at this, right? If you try to include one more, then you will see K plus 1 different pieces, right? Your capacity is K. Therefore, at least one page fault must occur. This occurs for every round at least, right? So you can conclude that it makes at least one page fault in a round. Okay? So this would imply that LRU is K competitive. Right? It makes at most K factor more page faults than optimum, right? right? Good. But this is not very satisfactory, right? K can be really large, right? Factor K is, you know, it's not that great. So, but the theorem is that any deterministic algorithm is K is okay. I think it's better to say no deterministic algorithm as a competitive ratio so no deterministic algorithm has a competitive ratio better than K, so which means that LRU is the best if you don't use randomization. Okay, and it's actually the example is kind of simple. So this is how I'm going to use construct okay, construct some okay. How do I show this, right? Remember in the rent or buy problem, right? Buy or rent problem. So we thought about adversary, right? Oh yeah, you rent until time t and buy, then okay. Then I just let you ski until the following day, right? Then you'd regret. Oh, if I just wait one more day, then I would not have bought it, right? So we are going to think about the adversarial strategy, right? How can you screw up the algorithm? So it's kind of simple example. So we have like say the first round is 1 through K, and I just explain words. So okay, so what's my strategy, right? So if you evict some page, I'm going to request it right away, right? So for example, if you say evict page 1, right? Then I'm going to request page 1, right? Immediately. You do regret, right? If you request page 3, I'm going to evict page 3, then I request page 3, right? So I can repeat this, right? Sorry. I should not put this one. Sorry. So new page request, right? So I'm going to evict say page 1. When I put this one, it means that I'm evicting this page 1, right? So for example, then okay. So so now I have a page 2, 3 through K plus 1, right? Okay. Now I request page 1, right? Then what do you do? Okay. Then you have evict something, right? Like page 3. So then I say request page 3 and so forth, right? Then at every time you are making a page fault. Okay? For every request you make a page fault. But think about the optimal solution, right? This can be confusing, right? Because you look at all the page, right? But you can see that in my strategy, I only use pages from 1 through K plus 1, right? Because whenever you evict page, I request it, right? And you see, I only use page 1 through K plus 1, right? So okay, so to make it view clear, I'm going to look at this page Q1. Okay, so minus Q1 means the page that is not requested in the round 1. So in this case, it's a K plus 1, right? Everything is requested except the page K plus 1, right? So if you look at here, there will be another page Q2 that is not requested in this way. Okay, then what's the optimal strategy here, right? Okay, in every round, okay, for example here, the optimal solution will just evict this page Q2 because it's not going to be used throughout the whole round, right? So you can check that it makes only one page fault per round. Make sense? Okay, so again, to recap, any determining algorithm will make K page faults per round, while as the optimum will make only one page fault per round. Okay. So yeah, so we will have to use their randomization again to get around this issue. Okay, we're going to use some notion chord marking. That's it. Sorry. What is marking algorithm? So it's kind of it combines it. I think the LRU has some nice, you know, it's nice in the sense that it makes sense, right? It seems good to actually evict some page, right? That was used a long time ago, right? So it's the right idea, but we want to add some randomness here, okay? So we are going to kind of simplify the simplify tracking the when they were used, okay? So that's the idea. So one, mark a page when requested. So in other words, pages enter cache marked. Okay, marked means that it was used recently. Don't touch it. Okay. When a page is to be evicted, choose uniformly at random among unmarked pages. But nevertheless, eventually we'll have to evict some page, right? Then what we do, because marked pages were recently used, I'm not going to touch them. So among the unmarked pages, I'm going to choose one, uniform random. And three, again, when page needs to be evicted, yet all pages in the cache are marked. Unmark all pages. Okay. So let's see. I think I can delete this, right? Maybe I can illustrate the algorithm using this, right? Okay. So what do I do here? So I'm going to put this, cache here, k equals 3, right? So when a page is requested, so okay, so it's page 45. So I fetch it, right? So and the page enters with marked. Okay, let's put this mark here. Okay, which means that it was used right away, very recently. Don't touch it. Okay. So then 3 requested. Mark. 5 is there. Nothing. 4 come here and mark. 5 is there. It's marked, right? 3 is it's used. No worry, right? And now it's time to evict a page. Okay. Then what do you do here? Oh yeah, sorry. Before that. Okay. So now because all pages are marked here, so I'm going to unmark. Okay. And then now to fetch the page P2, I'm going to evict one of these, right? But what do? I'm going to choose one of these and random because I don't know. I say suppose I chose like 5 here at random. Okay, so this 5 is gone and 2 I put 2 here. Okay, but 2 is marked. But now I see 9 here. Okay, I have to evict another page, right? But I'm not going to touch this 2 because it's marked. But I'm going to choose one of these 3 or 4 as the victim. Okay, so say I see evict this guy, then 9 is here, right? It's marked, right? And 3 is there. It's great, right? So yeah. Is there be something here? So I think oh yeah. Okay. Okay, so yeah, so there's no page fault, but when it's used, I mark it. Okay. Okay. So I should have said it. So when it pays, yeah, okay. I just mark a page when it's requested. Okay. Not only is there's a page fault. When a page fault is not, it doesn't matter. When it's requested, I just mark it. If it's already marked, just eliminate marked. Okay. But now it's at the end of round 2, and then now it's round 3 starts, right? And 5, we have page fault, right? But everything is marked, so we unmark everything, right? And the new round starts. Is that clear? Okay, this is the algorithm. Okay, so then, the analysis is kind of beautiful here. Right? It's if you see the idea, it's very simple, but it's very like elegant. So as you can see here, the first observation. At the beginning of each round, all pages are marked. Right? You saw this, right? So because it's you see, think about round 2, right? We all pages were marked, so I marked all of them. And then I use 3 pages, right? By definition of the round, I see 3 different pages, right? Therefore, I make 3 marks, right? So at the end of the round 2, so all pages are marked. I mark in the next round, okay, right? That's what this means, okay? Good. Okay, now I'm going to define old pages and new pages. So again, before talking about this, I need to fix. Let's fix around the I. Okay? So old pages okay, these are the page requests in round I plus 1. Okay? By the way, this definition has nothing to do with the algorithm. It just only depends on the instance sequence, right? So in this example, like what are all the pages, right? So if I look at this page, round 2, say this, I'm looking at this round 2, right? Then, okay, by the way, new page means the others. So 2 was not requested before, right? In round 1. Therefore, this is a new. 9, this is new, and 3, this is old, because it was requested in the previous round. Is the difference clear? Okay, I'm focusing on one specific round because I'm going to do round unless by round, and but I'm defining all the pages and new pages, right? By comparing the pages, right? By looking at whether those pages were requested in the previous round or not. Okay? Great. Like, let's see, let's quantify this number. So, let's use li to denote the number. Okay, excuse me. Number of new pages here requested in round I. Okay, obviously li is most k, right? Is for sure, right? Okay. So the first observation is okay. Sure, it's good. So we want to make some. Okay, so what do you want to say here? So again, we want to compare our algorithm to the optimum, but we want to have some. We have algorithms cost here. There's some optimum here, right? So like it'd be ideal to if you can compare our algorithm to the optimum solution. In this case, it's possible because it's not MPR the problem, right? But it'd be hard to compare because this optimum solution we know the whole the whole sequence, right? Somehow I need some kind of some low bound that's easier to compare to algorithm. Okay, so I need the new low bound. Okay, but the previous low bound we saw, like one page forward per round is just too weak. Okay, so we'll have to develop some stronger notion of a low bound. So we observe the following. Okay, so it's at least half times the sum of li. It kind of makes sense, right? Because C is y. So like let's look at say round 1 and round 2, right? So there are k different pages here, pages, and then there are li pages that are different from this k. Therefore, in these 2 rounds, there are k plus li different pages. Therefore, any algorithm will be forced to make else li page force. Okay, so what I observed is that if you look at round 1 and round 2, it'll make else L2 page force, right? And then if you look at round 3 and 4, it'll make else L4i and so forth. And also, if you also group, like if you look at only say round 1, and of course you get L1. If you look at round 2 and 3, you get L3 and so forth, right? So by adding up 2 and then dividing by 2, you get this. Okay, good. This is done. Now it's time to upper bound our algorithm's cost. So we are going to show this, right? Our algorithm's cost here, right? Okay, so let's this is so AI is number force by the algorithm in round I. Okay. If we show this, okay, by the hk is the harmonic number, right? Low k. So if you have this, then by adding up this by, we'll get hk times li most and most twice HK times optimum, right? Okay. So we are going to show that our algorithms cost at most twice of the harmonic number times the optimum cost. Okay, so remember that HK is just 1 plus over 2 plus 1 over k, which is roughly k. Okay, so let's focus on it remains to show this, right? That's the last thing we want to do finish before finishing this lecture. So it's actually simple, but it's a subtle argument. Okay, so I want to visualize this because this can be very confusing if you look at this. So like I would delete this again to save space here. So k minus li, and these are mu. These are odd. Okay. This is a round I. Okay. In round I, there are Li new pages, and there are k minus Li old pages, right? So I mean, they add up to exactly k, right? By definition of the round. And it's old, right? The old page means that they appeared in the previous round. So we're going to have this picture, right? So they were requests. The order doesn't matter here, but anyway, they were requested. These pages were requested in the previous round. Agree? There's a picture. Okay, so like for a while, let's assume that we don't really assume this, we don't need to assume this, but it kind of gives a better intuition of why this works. Okay, so now we want to show that even though like the optimum solution of the adversary constructs bad instance, still we're doing fine, right? To show that actually it turns out that requesting new page first it can only make only the algorithm suffer more. Okay, the idea is that the new page will evict some old pages, and then if the old pages are requested later, right? Then oops, we made a mistake, right? So that intuitively new pages are alive before old page will make the algorithm put in more trouble. Okay, but again, so but for now, just let's assume this, right? You can formally prove that, but let's assume that for simplicity, new page alive request and old page request. Okay, it's okay that new page requested in the middle, doesn't matter. But what I'm saying is that after this new page are requested, the old page are requested in this order. Okay, let's do this. Let's make this assumption, to make the argument simpler. Okay, so I'm going to focus on this specific J. This page J. Okay. So this is old, therefore it appears somewhere, right? Then what I'm going to show is this J's old page causes fault in round I is exactly Li divided by k minus j plus 1. This why? It's a okay. So if you don't know, then let's first look at the first order page. Look at this first page, right? Right. So what's the situation I'm looking for here? Well, one is requested at this point, right? But what's the chance that one is not in the cache, right? So which means that, okay, so when like some of these were requests, right? This guy, some of this guy evicted page one, right? Then one will incur page fault, right? What's the chance that one is not in the cache? Okay, so the cache size, k, right? Okay, and then so the new page, there are li new pages, right? It'll evict li pages. Okay, then what's the chance that j is here, right? It'll be exactly li divided by k, right? If j equals 1, it'll be li divided by k, right? Okay, make sense? I want to talk about the first page, right? When the first page is requested, why is it not there? Because unfortunately one was the one out of the li piece evicted, right? So li of k, so there'll be exactly li of k. Okay, so now the next one is like a little similar here. Okay, so what's the deal here? Okay, so now think about J. There are li pages, right? And plus J pages right here. Li new pages, J old page, right? Okay, let's think about this. And then it's confusing here. So okay, good. Let's think about this here. There are k pages. There are k pages, right? K old page here. But here we're thinking about J page, right? Okay, so we are thinking about k. Okay, cache of size k, and you're looking at the new page, li new page, and old page from 1 through j. Okay. But so out of k here, this old page, j minus, okay, except j. So j minus 1 page, or you think of remove this j minus 1 pages. Okay. Like so, like out of this k, from like denominator and numerator, okay, remove this j minus 1 pages from 1 through j minus 1. That's exactly what I get here. Okay, so I think I'm explaining very well. So I'll do a better job next time. I had a very clean argument in the morning, but I don't want to waste time here. Okay, so I'll continue in the next lecture.